तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Okay, so let me resume where we left off. We were talking about the microcanonical ensemble. I go over this argument again because it is a delicate argument, and it goes as follows. We have a large system A total, the total system which is isolated and in thermal equilibrium. And we are going to assume that it has some stated total energy E total, a total volume V total, and a total number of particles N total, and it is in thermal equilibrium. The energy is constant. Okay. And then I said, if we imagine partitioning this system into two pieces, and I call them A and B, these are subsystems which are in thermal equilibrium with each other, then the energy of either of these systems is not fixed because there are fluctuations. And if I now say that the energy of this is E, V and N, these are variable quantities in some sense, and then this is E prime, V prime and N prime. What we are going to do is to ask, given the postulate of equal a priori probabilities for all the microstates, accessible microstates of the total system, what can we say about the probability distribution of, for instance, the energy in this system? This is the question we are asking. And I said the probability that A has energy E, and I call this P of E, this was equal to, in the absence of any further information, simply the fact that all the microstates of the total system are equally probable. This is obviously that fraction of the total number of microstates of the total system for which A has energy E, and therefore B has energy E prime minus E total minus E. So this is equal to number of microstates of the total system such that A has energy E divided by the total number of microstates of the total system with energy E total or whatever it is, and that I denoted as sigma omega total of E total. This is the normalization factor, and this is more or less obvious, but now comes the physical assumption that these two systems have very large numbers of degrees of freedom each of them, and that the number of degrees of freedom in interaction on either side at any instant of time is very small compared to the number of degrees of freedom in the bulk in A and B. Then this quantity factors into P of E, factors into omega, which stands for the number of accessible microstates of the system A corresponding to energy E, multiplied by the number of microstates of the system B, which is omega prime, with energy E prime. And of course we know that E plus E prime is approximately equal to E total. What I have left out here is the interaction energy, which cannot be apportioned uniquely into either the energy of A or B, and my argument was that the number of degrees of freedom in this partition is very small compared to these guys, and therefore the actual interaction energy at any instant of time is very small and is neglected. So this was P of E, divided of course by the normalization factor. Okay. So this is where the physics has gone in, that the total number of microstates of the full system is simply the direct product of the number of microstates of this times the number of microstates of that, which is true if these are independent systems, but they are actually in interaction with each other, and again I repeat, the assumption is that the interaction energy is negligible compared to the energy of these two systems. Then this is true. This is the fundamental idea here. Now some idea of how big, oh by the way, this thing is a function also of V and N. I have omitted writing that, just for brevity, but there are V prime, N prime, and whatever other macroscopic parameters you need in order to specify this system. All of them are sitting there. Yeah.
So what is the meaning of interacting degrees of freedom?
You see, if there is a particle here which is attracting the particle there, then there is a potential energy of attraction, and now I am going to assume that these forces are short range forces, and therefore a particle here is not going to attract a particle there, essentially negligible, but close to the partition at any instant of time there will be some potential energy which can't be apportioned as the energy of this or that uniquely, and that energy is definitely needed. That is what is creating the interaction between these two subsystems, but it is itself negligible compared to E or E prime. So this is the assumption.
How many parameters are required to completely specify the macroscopic?
We don't know yet. We don't know yet. I am tending towards thermodynamic systems where it would depend on the energy, the volume and the number, because I would like to discuss fluids. I would like to make contact with thermodynamics. Of course if this is a set of charged particles, the electric fields, magnetic fields, you would need all of them, and we will add all of those as we go along. But right now I would like to aim towards the elementary laws of thermodynamics, which you would normally write down for fluids or gases or something like that. So just to be definite, I have said let us take E, V and N. I might need more. Okay, so given this, let us have some idea of how big these numbers are, how big this is likely to be, and let us do that by asking, okay, suppose I take a particle, a single particle, and put it in a volume V, and there is a particle moving around in this volume V. Let us calculate how many microstates it has. What is the number of microstates this object would have? Well, it depends on the energy, and the number of microstates is the number of cells in phase space of this object here, and of course the phase space is actually infinite dimensional, as you can see, because the momentum of this particle can run all the way from 0 to infinity in magnitude. Although the physical volume runs from 0 to capital V, it is inside capital V, the phase space volume is actually infinite. So we have to make the question a little more precise. I ask how many microstates, number of microstates of a particle of mass m with energy less than or equal to some number epsilon. So I prescribe an energy and I ask you, okay, within this energy epsilon, and it is a free particle inside, a single particle, no forces on it, what is the total number of microstates I could have? Well, what you do is to find the volume of the phase space corresponding to this total energy, and all you have to do is to recognize that epsilon is p squared over 2m. It is only kinetic energy. So I prescribe a limit and ask within this energy epsilon how many states do I have, and it is quite clear that the number of microstates, and let me call this omega, let me call this omega, omega would correspond to a particular energy, so let me call this number of microstates phi of epsilon. So this gives me the number of microstates of the particle such that the energy of the particle runs from 0 to epsilon. This number is equal to an integral over the volume element over V that is the dx dy dz to run over this volume element V, and then in momentum, so let me write this as d3r to show that it is a 3-dimensional volume element in coordinates d3r. I could write this in any coordinate system I like, spherical, polar, plane polar, Cartesian, whatever, times d3p in momentum space d3p of what, that is it, this is the volume, this is the volume here, such that this d3r is restricted to the volume V and such that modulus p is less than equal to 2m epsilon. So you integrate all directions of momentum such that the magnitude of this momentum is less than equal to the number 2m epsilon, where epsilon is what you prescribed. That is it, but this is an infinite number of points really, because each point is an element, is a possible state of the system, but we already said that we are going to count cells in phase space and you cannot specify x and p to better than Planck's constant in precision, and therefore this is divided by equal to 1 over Planck's constant cubed times this, because you are in 3 dimensions and each Cartesian component is an uncertainty Planck's constant and it is 1 over h cubed. Now mind you, I could have taken h over 2 pi, or I could have taken square root of 3 times Planck's constant, etc. So this is only giving you orders of magnitude, it is not giving you the actual number, which is irrelevant really. And what is this equal to? This is equal to V over h cubed, because this just integrates out, dV is just V, times this guy here, and what will I get here? How should I do this integral? Since the magnitude of P has been fixed, it is clear I must use spherical polar coordinates in momentum space, and then the angle is irrelevant, completely irrelevant, so this says this is equal to 4 pi times an integral from 0 to square root of 2m epsilon p squared dp. The magnitude of momentum, I call it p without any vector sign, and the 3-dimensional volume element is p squared dp in 3 dimensions, and then the angular integration has been done, that is a 4 pi, and the upper limit of integration is square root of 2m epsilon. So this is equal to, apart from some constants, this is proportional to V divided by h cubed, that is sitting there, and then the relevant portion is not the square root of 2m and so on, which we will fix later on, but p squared dp, and if you integrate this you get p cubed over 3, but the upper limit of integration is epsilon to the half here, and therefore epsilon to the power 3 halves. That is the key point, that the number of accessible microstates of this particle with energy less than equal to some number epsilon grows with epsilon like epsilon to the 3 halves. And where did the 3 come from? In this 3 halves, where did the factor 3 come from? It came when I integrated p squared dp, but where did the p squared come from? 3 dimensions. So this 3 is a measure of the dimensions, the number of dimensions you are in. If you restricted it to a plane, this would become p dp and that would become p squared and so on. So this 3 here is directly the number of dimensions, physical dimensions. And where did the 2 come from? Well, the 2 came because of this relation. The half came because this implied that P was proportional to epsilon to the half. The relation between energy and momentum, the energy was a quadratic function of the momentum. So the 2 came from there. The reason I am saying this is because if you change these assumptions, then that will change automatically. So this 2 actually came from the fact that the momentum, the energy is quadratic in P.
So is the energy equal to p square by 2m only in 3 dimensions, or is it valid even in?
That is a very good question. Is this true only in 3 dimensions or is it valid in all dimensions? it is valid in all dimensions. For a particle of non-zero rest mass, it is valid in all dimensions. Where did that come from eventually? It came from the fact that the right relation between energy and momentum for a free particle is in fact the following. Its E squared is c squared p squared plus m squared c to the power 4. That is the right relation between energy and momentum for a free particle, for a classical free particle in any number of dimensions. The moment you have this by the way is the rest mass of the particle. I am not going to denote this by m naught and so on, because then it gives you the wrong impression that mass changes with velocity. This is not true, this is not true. The mass is a constant, it is the rest mass, that is it. It is just that the relation between energy and the velocity and the momentum is not a linear relation in relativity. So since we are going to do relativity later on, we will get adopt proper discipline and just write a constant m. M stands for the rest mass of a particle. Now of course you also know immediately that this is epsilon is equal to m squared c4 plus c squared p squared to the power a half, and if it should so turn out, I take out a c by the way, so we can write this c and write this as m squared c squared plus p squared. If p is much less than mc, because the rest mass multiplied by the speed of light is a natural scale of momentum for a free particle, and it is called the Compton momentum that provides a scale of momentum for a particle. If the magnitude of the momentum of the particle is much less than mc, then you can do a binomial expansion here and you could write this epsilon equal to c times, I take out an mc, so there is an mc squared multiplied by 1 plus p squared over m squared c squared to the power a half, and that is approximately equal to mc squared times 1 plus p squared by 2 m squared c squared, that is the first term in the binomial expansion, plus half times half minus 1 over 2 factorial, that is equal to minus 1/8 p4 over m4 c4 plus dot dot dot, and you can see that this becomes equal to mc squared plus miraculously p squared over 2m plus higher orders. So there is a constant energy here called the rest energy of the system plus an energy due to its motion with a momentum p, and that is p squared over 2m plus terms which involve the speed of light, and if you set the speed of light equal to infinity as you do in non-relativistic physics and you ignore this rest energy because that is something you keep forever, matter can't be destroyed or created in non-relativistic physics, then the bookkeeping for the kinetic energy is just p squared over 2m, that is where you get this from. So this is the origin of this p squared over 2m. Yeah.
How would we calculate the integral dqp, because we won't have how would we use this symmetry to calculate
In how many dimensions? In n dimensions. In n dimensions again you need to have spherical polar coordinates in n dimensions, and the way you do it is there are n minus 1 angles of various kinds which run from 0 to 2 pi, one of them runs 0 to 2 pi, 0 to pi, and the other ones run 0 from 0 to 2 pi or whatever, and then apart from some angular factor which we can write down, finally you would have in n dimensions, n spatial dimensions, you would have p to the n minus 1 dp, that is the radial coordinate, and therefore when you integrate this out you get p epsilon to the power n over 2 here automatically.
So the rest energy mc square, is it the total energy because of the potential and kinetic energy?
No, this is a free particle, so I haven't added to it the energy that it might have due to experiencing a field of some kind. I haven't added that at all, it is just a free particle as it stands.
What that energy conveys,
Pardon?
What actually is that energy, how it goes, mc square?
That is the content of Einstein's theory of relativity, it says that a mass is equivalent to energy. Mass and energy are really two words for the same thing. It is not quite so simple as that, I will get back to this when I do relativity, but the point is this thing here, since it is not created or destroyed in non-relativistic physics, you keep that aside, it's just, it gets out of the bookkeeping both in the debit and credit side of the ledger. Since this is always there, you ignore it completely. But if there is a possibility of converting it or extracting that energy, then of course you have to keep track of it. The zero of energy is arbitrary for non-relativistic physics, but it's not so in relativistic physics, because the zero has a definite meaning there. Okay. So it's good to know that this 3/2 comes, the 3 come, where this comes from by dissecting it, the 3 comes from the number of physical dimensions, and this 2 comes from the quadratic relation between energy and momentum. If you should change this, then of course that whole thing changes. For instance, if you work in 2 dimensions, then it becomes 2/2. If you work in 2 dimensions with a system which has got a linear relation between energy and momentum, then that 2 goes away and you get an epsilon squared there, and so on. So each time we will be free with this, we will keep this in mind that this is where it comes from. And now you see, you can ask, what is this number of microstates for a given energy shell? Now you see what's happening is, in energy space, if this in momentum space, if this is the magnitude of the momentum and the momentum can point in any direction, the radius here was proportional to epsilon to the power half, and that is the reason the volume is proportional to epsilon to the power 3/2. Now if you ask how many states are there in a little shell of between energy epsilon and epsilon plus d epsilon, what would your answer be? It is the surface here, and therefore it is the derivative of that quantity there with respect to epsilon. So the number of microstates with energy in epsilon plus d epsilon in a little shell of thickness d epsilon about this would be equal to the volume of this shell, which would be the surface area here multiplied by this thickness here. And what is the surface area? That is proportional to epsilon to the half. You differentiate this with respect to epsilon, and it is equal to, is proportional to epsilon to the half d epsilon, apart from factors 2 pi's and so on. The crucial thing is this, that gives you the number of microstates in unit energy interval. When you multiply it by the thickness d epsilon, you get the actual number of microstates in that shell, and this has a name in a continuous spectrum. This quantity here, omega of epsilon, is epsilon to the half d epsilon, and this is equal to rho of epsilon d epsilon, and this is called the density of states. A very important concept. It is the number of microstates, apart from a constant of proportionality, it is the number of microstates per unit energy interval at energy epsilon, and that is growing like the square root of the energy in 3 dimensions. What would it do in 2 dimensions? This would become a 2. Had we lived on a plane, this would become a 2 and this would become just epsilon, and what happens to the density of states? Becomes a constant. The density of states becomes a constant, and this is of crucial importance for all these quantum Hall effects, fractional quantum Hall effects and so on, because there the electrons in these MOSFETs are actually effectively in a plane due to an intense magnetic field. They are confined to a plane, and then the density of states is independent of the energy. It has profound physical implications. What would happen in 1 dimension? Suppose we lived on a line, and this is important, there are actual quantum systems which are effectively 1 dimensional, then this would have become a half, and if I differentiate it, you get a 1 over square root epsilon. So therefore the density of states actually increases as energy becomes smaller and smaller. If you are in 1 dimension, things get more crowded and so on. So all these are practical implications in condensed matter physics, but for our present purposes all we need to recognize is that this idea of density of states, this guy here, is proportional to the square root of the energy. Of course you may say, look, we are going to do this next, when we do quantum mechanics, you put a particle inside a box, then the energy levels are not continuous, they are actually discrete. So where is the question of square root of epsilon as a number of density of states or anything like that? The answer is that in those cases, if you plot the number of states, if you plot phi of epsilon as a function of epsilon, in the true quantum case, what would happen is there is no state at all, there is a ground state, and then the first excited state is a little bit away from it, and then there is a first excited state, and the number just remains at that. So you start off, for 0 energy there may be no state at all, and then there is a finite ground state, so somewhere here it starts, and this is 1, and it continues like this till you hit the next energy threshold level, and then it becomes 2 and keeps going in this fashion. As the energy increases, the number of states, the degeneracies increase, the number of states increase, and so on and so forth. But what is the prediction made here classically? It says proportional to epsilon to the 3/2, which is a curve like this. So what is really happening is that as you get into higher and higher energies, then this ladder thing essentially starts mimicking your continuous curve. So the whole idea of a density of states, a continuum of energies, a continuum of possible states arises only if you have a sufficiently large number of the quantum numbers are large enough that you have many states, otherwise the continuum picture breaks down really. So if you go close to absolute 0, maybe only the first few excited states are involved, and then this is not a very accurate picture. But we are now going to do classical statistical physics, which is at high temperatures, sufficiently high temperatures, so I assume that things are continuous, energy is continuous. I have not brought in the complications of discrete energy levels at the moment, but I did bring in the fact that the number of cells in phase space is countable, and I did that by dividing by h cubed. Okay, so that was for operational reasons, so I ignored all those factors. I have this guy here, epsilon to 3/2, and now let us come back and ask, what is this guy, what is this going to look like? Omega of E, omega prime of E prime over, say, total of E total. What is this going to look like? What does this number look like if you do not know anything else? Well, there is a very large number of particles inside, n of them, and if you assume these are all free particles, then you can write the total energy as the sum of the energies of each of these particles. And then what would this look like? Notice I am using small omega there, I am using capital omega here. So a single particle I will use small omega, small epsilon, and so on, and for big thing here for the full system I will use the corresponding capital letters. So what would this omega be like? I know what this little guy is like, it goes like this thing here. What would the big thing be? Once again it is clear that if I write the total energy, if I write the total energy of the system as the first particle plus the energy of the second particle plus etc plus epsilon n, if there are n particles approximately, I write it in this fashion, then what is the total number of states that I would have? If these are all independent, the first particle can take 100 states, the second can take 100 states, it is clear that together they could take 100 squared states. The number of possible microstates is 100 square. So it is quite evident that E is proportional to for omega of E is proportional to E raised to a large power. This guy here raised to a large power, epsilon raised to a very large power, and if I say all the particles have approximately the same energy on the average, then n times epsilon is equal to capital E, and therefore instead of epsilon I will write capital E over n, and right now I am interested in the E dependence, so this goes like epsilon to something which is n here. In fact, since each of them is a half, this is n over 2, but n is so large I am interested in orders of magnitude at the moment, so let me just write this as epsilon to some alpha n. Alpha could be half or 3/2 or 5/2 depending on how I count, it does not matter, but the fact is it is proportional to n. And in fact if I write E epsilon in terms of n, this goes like E to the power alpha n. This is the crucial point. So let me repeat this argument. Each particle in this volume V has a large number of possible states. If its energy is some epsilon, then we know that the number of possible states it has is proportional to epsilon to the half multiplied by that resolution T epsilon. Now I have n of these particles, and I am assuming that these n particles, most of the energy of the system consists of the individual energies and the potential energy is negligible. If this is the case, which is not always true, but if that is the case, then I can write the total energy in this form, and if on the average all these energies are of the same order of magnitude epsilon, then the total number of states is epsilon raised to the number of particles. But epsilon itself is capital E over n to first order, to good approximation. So the whole thing is proportional to the energy raised to some constant of order unity multiplied by the number of degrees of freedom or the number of states, and that is a very rapidly increasing function of n of E. So this is the lesson that we need to know. These are astronomically large numbers. This thing here is of order Avogadro's number for macroscopic systems, and that is what you have to deal with here. So you have very large numbers, this is a huge number, that is a huge number, and when you have such huge numbers, then it is clear that what you should do is to work in terms of logs so that you bring things into a controllable fashion. And now what is going to be the most probable state? The most probable one is that state for which P of E is at a maximum, and that would be my equilibrium state. The system which has the largest number of accessible microstates, that is the macro state which is most probable. Therefore to compute the most probable macro state, most probable macro probable implies delta P of E over delta E equal to 0. It is at an extremum. Of course you should say, you should immediately object and say, well, you should ensure it is a maximum and not a minimum. We do that next, we will do that subsequently, but first it is at an extremum, means delta P of E over delta E is 0, and that is what I would say is going to happen in equilibrium. But then what does this mean? These are huge numbers here, and therefore since the log of a number is a monotonically increasing function of this number, I could as well take the logs and then take the delta. So it would be the same as saying delta log P of E over delta E equal to 0. Now that makes things much more manageable because it brings this huge exponent n down. And what does that give you? That tells you then that delta log omega of E over delta E plus delta log omega prime of E prime over delta E equal to 0, because this is constant, the denominator is constant. If I take a log here, this goes away, it is a log constant, does not get differentiated. So you see the normalization constant has gone off, and I am left with that condition there. But I also know that E total, E plus E prime equal to E total. Therefore E prime is E total minus E, and a derivative with respect to E is minus a derivative with respect to E prime, because the constants, because the two add up to a constant. Therefore I can finally write this condition as delta log omega of E over delta E equal to delta log omega prime of E prime over delta E prime. So that is the condition for the most probable macro state. That is what is going to obtain in equilibrium. Now notice the left hand side refers only to properties of A, the right hand side refers to properties of A prime. The right hand side may be a physically different system from the left hand side. You could have a jar of oil in equilibrium with an atmosphere, and that is fluid and this is gas, it does not matter. The corresponding quantities are equal on both sides. The rate of change of the log of the number of accessible microstates of system A is equal to exactly the same function on the right hand side for system B. So it says some system property of A is equal to the same system property for B. This system property is called the inverse temperature. This is the definition of the temperature. So we define a function. This is the definition of the temperature, and now of course I have to show you that this definition is the same as the thermodynamic definition, what you call the absolute scale of temperature, which was defined by saying the absolute scale of temperature is defined in thermodynamics by saying there exists a thing called the classical ideal gas whose pressure times volume is proportional to the absolute temperature. So I must show that this is the same as the ideal gas temperature, then the thermodynamic definition and the statistical mechanical definitions are identical. We have not done that yet. This is the definition for equilibrium. It defines temperature here. So I am going to define temperature and then say in equilibrium the temperature of A is equal to the temperature of B. That is the condition. So we define it, but what is the physical dimensions here? The physical dimension is not that of temperature. Omega is a number of microstates, so it is dimensionless. Log is of course dimensionless, but this is a 1 over energy. So I define a function beta of E equal to definition delta log omega of E over delta E, and that is the inverse temperature. So this beta of E is in fact 1 over K Boltzmann times T of E. Since we made the historical mistake of defining temperature rather than inverse temperature, which is what we should have defined, I call it 1 over K beta, and K Boltzmann is a conversion factor which converts from energy to temperature units. So you see, unlike thermodynamics where the energy is a function of the temperature in general, the average energy, in statistical mechanics the temperature is a function of the energy. That is the right way to do it. So this quantity beta, the inverse temperature, I am going to use very frequently. I will use the symbol beta here, but it is really 1 over kT out here. So what we are saying is that by definition in equilibrium the temperature of A is equal to the temperature of B. So this is the first condition, that when you have a large system, isolated system in thermal equilibrium, the temperatures of any two parts of it are the same, assuming of course that each part is large enough for you to talk about a temperature. If it is just one particle, then of course I can't talk about a temperature for it. So I have already assumed that both A and B are sufficiently large with a large number of degrees of freedom so that I can define a temperature, which is a statistical concept here. So I assume that omega of E is a continuous function of E and so on and so forth. By the way, this definition here permits you to go further than the normal definition of temperature would, because you see there is nothing to stop you from having a situation in which this omega of E, which is after all the number of states that you have, suppose it goes up and comes down, then the temperature could in fact become negative, because there is nothing that says omega of E must be a monotonically increasing function of E. For free particles, yes, it was increasing like E to some power, but there could be other systems which have some energy levels and then there is an upper bound on the energy levels. So you have lots of energy levels in between and then that stops, so the number of states would in fact go up and then come down again, and then the slope would become negative. So the possibility of negative temperatures is already built into this, and indeed there are systems which would display negative temperature in this sense here. So this is the statistical mechanical definition of temperature. It does not make much sense at the moment till we show that this is exactly the same as the temperature as defined in thermodynamics. Now once we do that, then we know that you are on the right track, and then you go further from there. But is this all the information we get? No, we get more information from here, because exactly the same argument would go for the other variables on which this omega depended, and the other variables here as I have written it here are the number and the volume. So in fact you can show now that delta log omega over delta V on both sides must be equal. And in fact delta log omega over delta n must be equal to delta log omega prime over delta n prime. Okay. And in thermodynamic terms, which we will see, this here, this guy implies that, this would imply that the pressure on this side divided by the temperature must be the pressure on this side divided by the temperature. Okay. I will show that this here really is the pressure over temperature. And what would this imply? What would that imply? So in thermal equilibrium for a very large system in isolation, the temperatures on the two sides of two parts of it are the same, the pressures are the same. What would this imply? This would imply that the chemical potential of this side would be the chemical potential on that side. So yeah, pardon me? We haven't yet defined entropy. We haven't yet defined entropy, but indeed you are right. I am going to define this quantity multiplied by Boltzmann's constant so as to get rid of this 1 over kT, the k Boltzmann. I am going to define that as the entropy. Yes. So jumping ahead a little bit, I am going to define the entropy of the system S of E as equal to k Boltzmann log omega. I am going to define the entropy in this fashion. Why do I do that? Because everywhere in physical physical applications it is log omega that appears, not omega itself. Therefore it is useful to have a name for log omega, and it is called entropy. It is a definition once again, and of course immediately you realize that this, since if this is a function of E, V and N, so is this a function of E, V and N equal to. So in general that is certainly true for such systems. Well, that is a good point. Since he has raised it, this is a good time to ask, what is the connection with thermodynamics? Well, let us ask what is the connection with thermodynamics. I am going to assume that all of you have studied thermodynamics, so you already know this subject. Yes? Fair assumption? So we do thermodynamics in 15 minutes, and then we, all you need to know about.
Assuming that the system with energy is in thermal equilibrium.
Yeah. Yeah.
But you started with that assumption and you are again getting back to the condition for equilibrium.
Yeah, so what I am saying is that in thermal equilibrium, system is in the steady state and so on and so forth, I made the assumption that all microstates were equally probable, period. The consequence of that was that certain partial derivatives of the left hand side must be equal to the corresponding partial derivatives on the right hand side. I could partition it further. So every piece of the system, if I define this function log omega, its derivatives with respect to these thermodynamic variables must be the same in all subsystems, and those derivatives I am now associating with physical quantities, thermodynamic variables like temperature, pressure and the chemical potential and so on. Of course these are definitions as it stands, but the proof of the pudding is that I am going to relate them to thermodynamic equations. So one way of doing this would be axiomatically to start from here and say this is my definition of PA, this is my definition of mu A, and to show you from here that you in fact get the ideal gas equation of state and so on. But we will not do that. Instead of that I will start with thermodynamics and show you get exactly the same relations, so it matches on both sides. I will in fact calculate this entropy, which you can't do in thermodynamics, compute this number, because we have the machinery to calculate it, because we know how to go to phase space and count cells, and therefore we know how to calculate it, which you don't do in thermodynamics. So let us go and do thermodynamics in a nutshell in 15 minutes. I am not sure what your impression of thermodynamics is, but it is a very basic science. It is the science of energy, which is the most fundamental quantity of all, so it is useful to know a few things about it, and going beyond the level of imagining that it is just a practice, gives you practice in writing partial derivatives or something like that. It is a little more than that. So let us write down thermodynamics in a nutshell. We will do thermodynamics for a simple fluid, which is the usual thing you do it for, and then we try to make it general for other complicated systems. I am going to assume the laws of thermodynamics. Of course the laws of thermodynamics are derivable from here explicitly, but we are going to assume it and just make sure the matching is right. Now what is the first law of thermodynamics? It is essentially a conservation of energy, and what does it essentially say? It says that if you supply some heat to a system, you call it dq, is the amount of heat, infinitesimal increment in heat that you supply to a system. This heat goes into doing two things. First, the system does some work possibly, and the second thing it does is to change its internal energy. This is the statement. So dq is du plus dw, this way you write it. Now of course wisdom tells you, a lot of experience, the whole of the 19th century tells you that unfortunately dq is not a perfect differential. In other words, you cannot specify the heat of a system q without saying how it reached that state. So specifying the value of q at some values of thermodynamic parameters is not going to tell you anything. Similarly for w, but not true for u, which is a state function, which means if you tell me the independent variables, perhaps s, v and n or whatever it is, then I can tell you a unique u, but that is not true for dq and dw, and you recognize that by putting little slashes here to show these are imperfect differentials, these are not perfect differentials. But the miracle is the difference between dq and dw is a perfect differential. So that is why more sensibly it is better to write this du here as du equal to dq minus dw and say this difference, but this is how it got written initially, so we leave it at that. Now what is this dw? This is equal to du plus, it is equal to pdv for a simple single component fluid. So let us put that down, plus pdv, since we are familiar with that, so let us put the pdv. But actually this system could do other kinds of work. It could be charged and then it would do work against an electric field, for example you apply an electric field, it would do work, or it could be magnetic, you apply a magnetic field, its magnetization could change. So there are lots and lots of kinds of work that you have, and in general this thing here has a better way of writing it. You should write it as some force times a displacement. This is essentially what pdv is, some force times a displacement of some kind, but then the way it has been written, it is clear that if dv is positive, P decreases. As you know, if you compress something, you increase the pressure, the volume decreases, and therefore this pdv is got a wrong sign in some sense. The right way to do this is to write this as du minus a summation over all possible forces with their conjugate variables, thermodynamic variables. So let me write this as fi dxi, and these quantities are generalized forces and these fellows are generalized fluxes. Of the forces, P is a very important example and the corresponding dx is minus dv. But there are other terms that are possible. You could, for example, have a force that is not physical at all, called the chemical potential, and then what changes is the number of particles. So you could have a term like in single component simple fluid would be dq equal to du plus pdv minus mu dn. That is the simplest generalization of the most elementary way of writing thermodynamics for a single component fluid. There the only work you do is the pdv kind of volumetric strain. Incidentally, what is P? What is P? What does it stand for? The pressure, but it is a macroscopic body, so you really have stresses and strains, and a stress is a tensor of rank 2 because you can have uniaxial stresses and you can have shear stresses. And what is this P then? It is the volumetric strain, it is a hydrostatic stress. In other words, it is the trace of the stress tensor, trace of the stress tensor. So you really have a stress tensor sigma ij. Sigma 1 1 would correspond to pulling in the one direction, 2 2 would be in the 2 direction, and 3 3 in the 3 direction, and then sigma 1 2 would be a shear perpendicular to the 3 direction, and 2 3 and 3 1. So you have a lot of these guys. It is a symmetric tensor of rank 2, but if you took sigma 1 1 plus 2 2 plus 3 3, that is the hydrostatic stress, it is the trace of the stress tensor. Now the trace is independent of rotations, right? Therefore the pressure is a scalar. Since it is independent of rotations, you have exactly the same value no matter how you orient your coordinate system. That is why if you put inside a fluid, you put a little volume area element, it does not matter in which direction you put it, but the force per unit area is the same. What do you call that? What do you call this rule where the pressure inside is the same in all directions? Pascal's law. Pascal's law. Pascal's law is a statement that the stress, that the pressure is a scalar because it is the trace of the tensor, stress tensor. It follows directly from there. The medium is isotropic as in a liquid, and then immediately it follows that the trace is independent of how you orient this. Otherwise you would have to have different pressures in different directions, which you could have in a non-isotropic medium. Okay, so that is the pressure we have here, and then there is this chemical potential and N and so on and so forth. But remember, this is the generalized form of writing it. For the moment let us write this for a single component thing. So du plus P dV minus mu dN. By the way, let me call this the energy E and not U, because U I should like to reserve, which is the same thing in thermodynamics, for the average energy. So let me just make clear that this is energy E, so write it as dE. When you do thermodynamics and when you have average energies, then it is exactly equal to what you call the internal energy, but to remind myself that it is the energy I write E there. And on this side, what is this equal to? What is dq? The second law of thermodynamics says that dq we know is an imperfect differential, but in the case in which I have reversible processes, then I can use an integrating factor on dq to convert it to a perfect differential, and in thermodynamics that integrating factor is called 1 over the temperature, because we know that dq divided by T becomes equal to ds, the change in the thermodynamic entropy. Okay. That is the definition of the entropy, the increment of the entropy in thermodynamics. So if I put that in, it says Tds equal to dE plus P dV minus mu dN, which I will write in the following form: d over T, P over T minus mu over T. Now yeah, it is reversible, so I am going to assume we are talking about reversible processes, otherwise I do not know how to define entropy in thermodynamics.
Even the pressure PdV would be only for reversible.
Pardon me?
The PdV term for the,
yeah, we are going to assume that everything is in quasi-static equilibrium, everything is reversible and so on, otherwise you can't even point on the PV plane, you can't even write these things down. Everything is in thermal equilibrium, quasi-static processes and so on, very slow compared to the equilibration times. Then this is certainly true, and by the way, what does this tell you? This tells you that delta S over delta E, keeping V and N constant, is equal to 1 over T. And if S is k log omega and I bring the k down, then it says delta log omega over delta E, keeping V and N constant, is 1 over kt, and that is exactly what you have here. So this is built, this is tailored to make sure that you get that right, or rather that follows from this, follows immediately from this. Okay, this is not a rigorous proof, but you see that, and incidentally that is the reason I got P over T and mu over T, because they are just partial derivatives of this entropy with respect to V and N there immediately. This is called the entropy representation of the microcanonical ensemble, because it writes the infinitesimal, it writes the differential of S in terms of the differentials of E, V and N. So this says S equal to S of E, V and N, and this is the entropy representation. You could rewrite this in another way. You could write this as dE equal to TdS minus PdV plus mu dN. You could write that too, just as good, and this is called the energy representation of the microcanonical ensemble. Which you choose is a matter of taste. Then of course you have all these partial derivative relations. It says immediately delta S over delta E at V and constant is 1 over T, similarly definition of P and a definition of mu, and ditto here you can write delta E over delta S is a definition of temperature and not its reciprocal, and so on. So all the usual relations could be written down. So much for the first law here, but notice one thing. Notice that when you write this, when you write the increment in the energy in terms of quantities here on the right hand side, thermodynamic quantities, they occur in pairs, conjugate pairs, almost like your P's and Q's in Hamiltonian dynamics. They occur in conjugate pairs. There is a T and an S, a P and a V, a mu and an N. The product of the two has dimensions of energy always. So the product of a generalized force times a generalized flux has dimensions of energy, but the individual force flux may have all kinds of physical dimensions. Similarly you could add terms to this. If you had an electric field, you would have E dot dP, the energy, the electric field times the polarization, that will have physical dimensions of energy. Similarly B dot dm, where B is a magnetic field, M is a magnetization, would have physical dimensions of energy, and so on. But in the simplest case, this is the rule that we have written down here. These are conjugate variables in that sense, but there is another very crucial thing that you notice, and that is some of these variables change with system size, some variables do not, and always they occur in pairs. If I take a container containing volume V number n particles and double the volume, double the number of particles, keeping the density constant, then the density does not change, the temperature does not change. These are intensive variables. Things which become proportional to the volume or the number of particles are extensive variables, and this breaks up neatly into intensive times extensive. Pressure is an intensive variable, chemical potential is an intensive variable, the entropy, the volume, the number, the energy are all extensive variables. So we immediately have a breakup into intensive and extensive variables. The other thing is, there are certain things you apply as generalized forces and certain things you measure as fluxes, as responses. So immediately you see that there is a response, stimulus response relationship here. T, P, mu are called field variables, and S, V, N are called state variables, they are extensive. So it is like you apply the field variables and you measure the state variables. Of course this distinction is not always rigid. If you take a container of gas, I could put a piston on it, I could do two things. I could increase the load and change the pressure and thereby change the volume. I could also remove the piston, change the volume and thereby change the pressure. So which one you call the force and which you call the flux is actually a little up to you, but in general you would call the field variables, the intensive variables, the field variables, and the extensive variables, the state variables here, and they occur in pairs here. So this is it for thermodynamics. All the Maxwell relations blah blah can all be written, but there is one crucial input that is missing, this is not telling you enough, and that is we have not used the fact that the energy is an extensive variable. If I simply double the number of particles, double the volume, etc., and do not do anything else, I would in general change the energy, and it is an extensive variable. I am going to put that in next time as an input. I am going to assume that the energy is a homogeneous function of degree 1 in those variables S, V and N, and then use Euler's theorem from calculus to derive the rest of thermodynamics. So that is it, and once you put that along with this, the job is essentially done, and then we make contact with what we come back here and make contact with this. The rest is a matter of detail as we go along, but this is the target. So we meet next time and then I do this.